All right, last but not least, we have the trough. Trough is 11 feet long and its ends have the shape of isosceles triangles that are 3 feet across the top and had a height of 1 foot. So isosceles triangles, awesome. Probably not going to draw this to scale. But there is our trough. Let's see. 11 feet long and 3 feet across the top and have a height of 1 foot. Yeah, it definitely did not draw this to scale. That's okay. All right. So that's what it looks like. And it's being filled with water at a rate of 14 cubic feet per minute. How fast is the water level rising when the water is 4 inches deep? Okay. So what I'm going to do is I'm just going to kind of represent that what's happening is you sort of have a trough within a trough, right? Or a prism. This is a prism shape. You have a prism within a prism. You have the trough is one prism, and that is a fixed shape. But then you have the prism of water that is inside this trough. It has the same shape. Its bases will be isosceles triangles, but it's ever changing. It's ever increasing in size. So let's look at what we know. It's being filled with water at a rate of, so that appears to be dV dt. And again, it's the volume of water. It's the volume of the trough of water that is increasing at a rate of 14. And what do we want? We want to know how fast the water level is rising. So there is let me use maybe red. This would be my water level. There is a height here. And there's also a radius here, or I guess you could call it a width. Maybe a width would be better. I'm going to erase that. Of course, it's going to erase my water. So there is a height and a width to your trough of water, to your prism of water. And what we are looking for is the HDT, how that height is changing at the moment when H is what? It's not 4. Why is it not 4? Look at your units. The entire trough is only 1 foot deep. So it can't be that I'm asking for when that, how fast is it rising when it's 4 feet deep? It's 4 inches, which would make it 1/3 of a foot. Okay. Okay. So we need to come up with an equation that relates the volume of this trough of water to the height of this trough of water. So again, this is the kind of thing I would probably give to you because you may not remember, but I'm going to just remind you that the area of a prism, or sorry, the volume of a prism is the area of one of its bases, because the bases are equal, times its length. Right? So the area of the base would be the area of that triangle right here, right? The area of that triangle would be 1/2 base. Well, the way I've written it, the base would actually be 2W times the height, because I wrote the W to just be, I should really be using red for this. I wrote the W to just be half of this height here. Times the length, which is 11. So that would be WH, whoops, 11 WH, which is not a nasty equation at all. But here's the problem. What do we know about volume? Okay. And what do we want to know about? Height. What do we know nothing about? W. So if I leave this W in the equation and I try to take a derivative, I have no information about W dt. So our issue here is that we need to eliminate the W before we differentiate. And that's because we don't know or want dW dt. That almost says no. And it said something similar to no. Okay, so this is what I was referring to in the very first video about needing to eliminate a variable. And the way we're going to do it is also from similar triangles. So I'm going to zoom in on this one base. And I'm going to fill in, this is the water level that we talked about here. Right? And then we also know that the height of the whole thing, so this whole, whoops, that was bad. This whole height was 1, right? And what about this? It was 3 across the whole top. So if I'm just going to look at half of it, that would be 1.5, right? So do you see the similar triangles coming in again in exactly the same way they did before? I have W, base is to base, as height is to height. And I'm trying to get rid of the W, so I'm going to solve that for W. And then I'm going to substitute that in right here. So I have volume equals 11 times 1.5h times h, which is 16.5h squared. So now I have an equation for the volume of the water that's in the trough, and it's based solely on the height of the water in the trough. So we're ready to differentiate with respect to t. What's 16.5 times 2? 33, I think. I hope. I will plug in and solve. So 14, whoopsies, not 144, 14 over 11. And that will be what, feet per second? Is my change in the height of the water. Ooh,